All right, we're live. Hey, good afternoon, everybody. This is Lieutenant Bob Roberts with the Greenville Squadron. Tonight, what we're going to be doing is we're going to be covering the start of the Dimensions modules, the Aerospace Dimensions modules. The very first one is called Introduction to Flight. That's Chapter 1. And let's see here. Let's get right into it. Let's see, we got PowerPoint. And again, Aerospace Dimensions. So Aerospace Dimensions, there's a total of 6 books. The way that they wrote these books is that you can do any of them in any order. So this way, if you're at a squadron and if the squadron themselves are doing it in, say, book 5, you don't have to start all the way at book 1 and go to book 5. You can just start at book 5. And so for the sake of the video series, if you're following along live with me, we are going to go in order. So we are going to start off in book 1. Now the book 1 has 3 chapters. So tonight we're going to be doing chapter 1 of book 1. And with that, let's go ahead and get started. All right. All right, so the Aerospace Dimensions, as I meant, each one of them stands on their own. And so this way, if you wanted to start on book 4, feel free to start on book 4. If you want to start on book 1 with us, go ahead and start on book 1. You can see here, this is what the book looks like. And here's how I think that you should use the video series. So my recommendation is that you read the material first. Use the video series as a supplemental to help reinforce what you've read. Sometimes you might have questions when you read something, and then if you hear somebody explain it, your brain kind of kicks in. If you already knew the material, you hear somebody say it again, it just kind of locks it into your brain a little bit more. So I recommend that you read the material first, make some notes, highlight the different sections that you think are going to be important. Go ahead and watch the video series, and then go ahead and try some of the hands-on lessons. Once we get through the this video series, I'm going to come back and I'm probably going to do some of the hands-on lessons. But go ahead and you can work on the hands-on lessons on your own. Most of them are pretty simple. You can usually use the supplies you have around your house. Go ahead and do that because it makes you think about the objectives a little bit more and locks it into your brain. And then lastly, reread your notes and then go take that quiz. Go get 100 in that thing. All right, so the learning outcomes. So we have some learning outcomes. Here's our outcomes for Chapter 1. Chapter 1 is called Flight. I'm going to read this on the bottom. So the first, we're going to go at the very end of the video. We're going to talk about these again. So describe the relationship between Bernoulli's principle and Newton's laws of motions and how they were used to develop a machine that could fly. That's going to be the first one. Second one's going to be describe the coefficient of lift and the parameters involved. The third one's going to be identify the parts of the airplane and an airfoil. The fourth one's going to be describe the 4 forces of flight. And the fifth one's going to be to define the 3 axes of movement around those axes and the control surfaces that create that movement. All right, so let's get started. So the very beginning, I want you to really think about what does it mean to fly. So if somebody were to say to you, give me a one word that comes to your mind when somebody says fly, what does that mean? Think about this. If you want, go ahead and pause the video. If you're not watching live, go ahead and pause it. Think about it. What one word comes to your mind when you hear the word fly? Have you ever dreamed of flying? So back in the ancient days, there was a famous story of a father and son. Daedalus is the father, Icarus is the son, and they were imprisoned on the island of Crete. Now, they were adventurous folks, and rather than just stay on the island of Crete, imprisoned for the rest of their life, they wanted to get off. So what did they do? They went around, they found wax. And then they went around, they saw all the feathers that had fallen off the birds. And they put the wax all over their arms, and they put all the feathers all over their arms, and they just started flapping a lot, right? Well, they flapped so much that they rose up into the sky, and they started flying away from the island of Crete. And unfortunately, the son, Icarus, was a little bit adventurous. And so while his dad, Daedalus, was flying close to the ground, Icarus started flying higher and higher and higher. Well, his dad was telling him, hey, don't go too high. Well, his son didn't listen, and he got a little close to the sun, and all the wax melted off his arms, and he crashed in the ocean. He died. It's a Greek story. So everybody dies in Greek stories. So here's the question. Do you believe that story really happened? Yes? No? Why not? Why or why not? Maybe you do believe that story happened, why do you believe it happened? So how do birds actually fly? So, birds have been flying for a long time before we've ever flown. And so one of the things that's important is that birds are masters of the sky. They're not really that great on the ground. They can kind of hobble and hop around, but they're not really all that fantastic on the ground. But you put them into the air, and they're really quite impressive. Well, their wings operate in two ways. So when they're going at good speed up into the air or against the wind, their wings operate just like an airplane wing. They have lift, and it helps keep them in the air. When they're on the ground or when they're going too slow and they want to get into the air, they can twist their arms and their feathers, and they can grab the air and shove it down. And then that helps you. Basically, they can use their wings as we would use a propeller on an airplane. So that's how they can fly. There's some really fantastic YouTube videos out there going into great detail. Mankind has been studying birds forever, trying to learn their secrets and how they're flying. So here's a question. So we can run and we can jump. Why can't we fly? What is it about us that we can't fly? So to help us answer that question, we're going to take a look at two famous scientists that really are instrumental in us being able to fly, although these individuals never actually flew themselves. So the first one was Daniel Bernoulli. He came up with the Bernoulli principle. I've got that on the slide here. I don't expect you to know this. I did figure this out on my own, figure out how to use it, and it is actually pretty fascinating. However, so if you're really like somebody like later in high school, or you're just some whiz kid, go ahead and try to figure out this equation. You can find some other YouTube videos that will focus just on that equation, and you can see how it works. Really, what it comes down to though is that where pressure is least, velocity is greatest. And so the other way of looking at that is, as the faster you go, the faster the air goes, the pressure is going to be least. So pressure is least where velocity is greatest, and pressure is greatest where velocity is least. So what does this mean for flight? So if we take a look at a wing, a normal wing of what we consider, we can see that the air over top is going faster. And since it's going faster, that means we have less pressure. And the wind underneath the wing is going slower. And since it's going slower, it's providing more pressure. While since there's more pressure under the wing than on top of the wing, that's going to lift the wing up. That is one factor of lift and flight. Now let's take a look at Sir Isaac Newton. So if you're in CAP any amount of time, or if you're in science any amount of time, you're going to hear about Newton's three laws of motion, of gravity, motion, all the time. So the three laws of motion, and Newton gave us those laws. And the first one is an object at rest will remain at rest unless acted upon by an unbalanced outside force. So what does that mean? So if I have, if I'm holding a ball, if I'm in space and a ball is just hanging out there, if I push it, it's going to just, it's going to go forward. If the ball was already moving and I push it, then the ball will slow down, stop, or go the other way, depending on how much, pressure I put on it. So that's why when we throw, if you have a game of baseball and if somebody throws a baseball, that bat weighs a lot more. So that ball may be going, 90 miles an hour or more if it's a fastball. But the person swinging the bat, that bat weighs a lot more than that ball. And so when the bat hits the ball, there's a lot more force going in the opposite direction. That's why that ball will immediately stop. If you've ever seen a video of the ball stopping, it's actually pretty neat. It will actually just squeeze together into a weird shape and then take off. And so that's Newton's first law. So number two, a force acting upon a body causes it to accelerate in the direction of the force. Acceleration is directly proportional to the force and inversely proportional to the mass of the body being accelerated. I think that one's pretty self-explanatory. And the third one, this is the one that we care about for aviation the most. We care about all of them, but the third one's the most. So for every action, there is an equal and opposite reaction. So when I hit, I will use that baseball analogy again. If I hit that ball, that bat is going to keep it's going to push that ball out and hit it away. So we changed the force. Now that bat, if you really feel it, even though the bat weighs a lot more, so it'll overcome this. You can tell when that bat hits the ball. It will vibrate the bat. And if you were measuring the actual bat itself, you would see that the bat slowed down just a little bit because it's getting an opposite reaction from the ball. And so these are the two scientists, Bernoulli and Newton. And so they helped define some of the science that helped us figure out how to fly. Now, there is two sets of brothers that really did the most for flight in the very early ages. So Joseph, and I'm probably going to butcher these names, but Joseph Etienne Montgolfier. Most people think that they were the ones to do the very first powered flight. They created a hot air balloon, and they flew it over Paris, France. And that was for 25 minutes, and that was November 21st, 1783. Nearly 100 years later, Orville and Wilbur Wright, they are credited as inventing and building and flying the world's first successful motor-operated airplane. Amazingly, the Wright Flyer, and if you are in the United States, and if you ever go to the Aerospace Museum downtown, it's not the one at the airport, but the one downtown, they have a replica of the Wright Flyer there. It's pretty amazing. Let's see. So the next. All right. So now we're going to actually look at lift. And so really quickly, one of the things I want to talk about is that when we talk about lift, we are, for a long time, and I'll be honest with you, I'm not all that old, even though I seem like I get older every day, but I'm really not all that old. And so I got my pilot's license, 23 years ago, give or take. So it's not, hundreds of years ago. So 23 years ago, my primary flight instruction book, I actually went and looked it up, and it said that, when the wind hits the wing, it separates, and then the top goes faster, and it'll meet up with the wind on the back of the airfoil, and then they meet up, and then they go out. It's actually not true. So what we have is we're going to show a short video here, and we're going to actually talk about the fact that the wind over the top actually goes faster. So let's go ahead and listen to that real quick.
It's often said that lift on a wing is generated because the flow moving over the top surface has a longer distance to travel and therefore needs to go faster. This common explanation is actually wrong. This video shows that the air on the top does move faster, but it doesn't reach the end of the wing at the same time as the air along the bottom. Here we use smoke to visualize the streamlines around an airfoil. We can pause the smoke by briefly interrupting the supply. This gives us lines that travel through the flow, as we can see here. And if we now slow the video down, you can follow those lines, and that gives you an idea of how fast the flow is in different parts of the airflow. Here you can see it speed up as it approaches the airfoil, and it moves faster over the top compared to the bottom. You can see that it reaches the end on the upper surface much earlier than it does on the lower surface. In fact, by the time it reaches the end on the lower surface, the flow's already gone a long way past on the upper surface. This shows very clearly that the flow doesn't take the same amount of time to reach the end of the wing.
Okay, so I think that's pretty fascinating. Now, one thing, and thanks for the folks at Cambridge for that video. Appreciate that. Now, the one thing I want to really point out is two things. So one, you get that airflow, it comes off of the wing, and it slides down, right? So opposite reaction. So if the wind is pushing down, what is the opposite reaction? The opposite reaction is the push up on the wing itself. And so that's where a lot of the actual lift comes from. It comes from that downdraft. So now we want to take a look. And the other thing I want to point out too here is, we've been flying in airplanes now for well over 100 years. And we've gone through some pretty amazing things. If you think about how we've come from that Wright Flyer, from the Wilbur and Orville Wright, to spacecraft and jet fighters and big, huge airliners where you can sit in a seat and travel hundreds and 500, 600 miles an hour, through the air from one continent to another in this world. Really pretty fascinating that we did all that in such a short amount of time. But the amazing thing is that we're still learning it. They're still determining how flight actually works, figuring out all the little rules and the laws of physics for how lift works on a wing. And so it's pretty fascinating. So if you were somebody that wanted to get into aeronautics and really wanted to get into the science of flight, there's still a lot of room for you. It's not like we've figured this out. So this is still very much a new science that we're still spending a lot of time on. All right, so let's go ahead and let's take a look at the next slide. All right, so why does the air stick close to the wing? So if we take a look at a wing, why doesn't the air just kind of hit that top and just go straight off, right? Why does it stick down? Why does it stick onto the wing? Because if it didn't do that, then it would actually push the wing down, right? It wouldn't provide the lift, right? So it slides down. That downdraft is what helps lift up the wing. So why is that? So I want to show this video, and this will be the last video that we show. But I couldn't think of a better way to explain it. I actually spoke to this professor because he has this mirror. And if you're in the Greenville Squadron, we're actually going to try this. I actually have one of these special mirrors that I bought. This mirror was $30. The mirror that he's going to do this experiment on is $3,000. I'm trying to see if the company will lend me one. So far, I haven't heard back. But this really is fascinating. So here, watch this video.
What do these two things have in common? The Coanda effect. We can use our Schlieren optics setup to actually see how the air flows past an object. Here's a cylinder, cardboard cylinder, and my source of air is going to be simply a hair dryer. And as I bring the hair dryer closer and closer, you see the flow of air is straight, but when it is close to the object itself, the air gets deflected downward. It follows the contour of the cylindrical object. When it's far away, it goes straight. This is true for any object. Here's a spherical object, a basketball. Again, if I bring the airflow close to the basketball, notice how it gets deflected downward. It tends to wrap around and follow the contour of the ball.
And so this is what we see on the airplane wings.
Notice when the air is far away from the ball, it just goes straight, whereas as I get closer and closer to the ball, it actually follows the contours of the ball and curves around. What's going on? Why does it do that? Well, we can understand it by assuming there's friction between molecules in the air. We call that viscosity. So if you assume for a moment that the air is going to go straight and not deflect, molecules that are sitting underneath the airflow feel a friction force to get dragged along with the airflow and leave that area, producing a reduced pressure area here. And it's reduced compared to what's up above. And so there's a net force that pushes the airflow down and it continues to curve around the ball. And that's the Coanda effect. Let's have a look at a ping pong ball being supported by a jet of air, again supplied by our hair dryer. Notice as I tilt the hairdryer, the ball remains in the stream of air and is still levitated, but also notice how the bottom of the ball is deflecting the air so it wraps around. The air follows the contour of the shape of the ball. It's really annoying when
Okay, so that is the Coanda effect. So let's see, let's go to the next screen here. Yeah, so that's how we get the downdraft off the wing. I've been looking at aviation and education for aviation for a long time. I've never seen that before. I really felt that was fascinating. So it does. You can literally. There's a way with the cameras nowadays to be able to see moving air. That's pretty amazing. So all right. So a couple things. So now that we know about that, we have to look at the angle of attack. So when you have the angle of attack, the airplane's sitting on the ground for the most part, the nose is pointing straight ahead, and as it takes off, you lift it up. Now you're going pretty slow at this point typically, right? So your lift is going to be a couple things. You're going to have lift on the wing. It's going to be lifting that way and up. And then you're going to have the thrust, right? So the thrust is going to be pulling this way, and that's going to help you as well. And so as you go up and down, you're going to have that angle of attack. And so that's going to change where all that backdraft is coming down. So the more the angle, you're going to have more air coming underneath the wing, helping to push it up. You're going to have the lift of the wing, lifting it up, and you're going to have that backdraft. So these are all coefficients of lift. So it's not one thing that's making that airplane fly. There's several. And you have the thrust pulling it up. So that's a coefficient of lift as well. So that's also why when an airplane flies upside down, it can still fly. It still has the air underneath the wing pushing it up. It still has the thrust. It still has the downdraft from the underneath, from the bottom side, or now it's the top of the wing. You won't get as much lift, but also if you look at aerobatic airplanes, if you look at their wings, they don't have it where it's like flat on the bottom and rounded on top. It's rounded both on the top and the bottom. So this way they get the same amount of lift. Doesn't matter. They're upside down or right side up. If you tried to go upside down in a Cessna, you would have to pull the nose up a lot higher to compensate for that difference of that one part of lift. Since the curve of the wing is now on the bottom, you'd have to compensate by making the nose higher or giving it a lot more gas, making the engine work more. So that's how the coefficient of lifts work. Let's go ahead and look at our next page. Okay. So the four forces of flight, we've been talking now about lift quite a bit. I think you've got that. Everything that's sliding through the air or a liquid, there's drag associated with that. If you were to stick your hand out the window when you're driving, you'll feel the wind pushing against your hand, making your hand fly backwards. Also, if you're out driving down the road, your parents are driving the road, go ahead and try to make your hand different shapes. There's times like I get bored, like I'm driving a long distance. I put my hand out the window, and if I go low, my hand goes down. If I go like this, my hand will fly like right up. But you can feel the drag from the resistance going from the air or liquid going across your skin. Thrust, in this case, this is a jet, so the jet engine is pushing it forward. If you're in a propeller-driven aircraft, the propeller is spinning and it's pulling you forward. And so the natural forces that you have are drag and gravity, weight. You get those no matter what. And the two artificial forces that are because we're doing something is the lift on the wing and the thrust. So you can control thrust, you can control lift, you can't control drag. You can try to make something smoother, but whatever the drag is what the drag is, and it weighs what it weighs. So when you're up in the air, you can't control drag, you can't really control gravity, you can control thrust and lift. Okay. Now, one thing I'd like you to do is go ahead and think about the forces on other objects. So I picked two here. I picked roller coasters and cars. And then some individuals on the internet, they put some arrows showing the different forces. Go ahead and take a look at these two. But what else can you think of? It's fascinating, just like if you were in a car driving and you take a sharp corner, your body, you feel like your body's sliding from one side to the other. Think about what the forces are on those tires. Think what the forces are on your body. If you're in my classes, you will or have heard about gyroscopic precession. So think about that as well on the wheels of the car. So, all right. So we're getting pretty close to the end here. So we have the three axes. We have lateral, longitudinal, and vertical. Lateral is nose up, nose down. Longitudinal is your rolling, so that's your ailerons banking left and right. And your vertical is yawing, so that's the big tail. Can move it this way and this way. Or in aviation, we call it step on the ball. So that'll help move it to keep the airplane kind of turning nice and even as opposed to sliding out or slipping in. So these are the three axes of flight. And let's see here. So the lateral is controlled by the elevator. So that's the fin on the back of the airplane that allows you to go up and down. The ailerons control the pitch. And the rudder controls the vertical. Now flaps are interesting. So when you lower the flaps, you're doing two things. One, you're increasing the amount of surface area of the wing. So you're making a longer distance going off the top. It's more angled down. So that also means that you're getting more downwash. So you're getting more lift. Now we put those at the inside of the airplane because when do we use flaps? We use them when we're slowing down. We want to land. We want to be able to control the airplane at slower speeds. And so the outside tips of the wing, that's where ailerons are. So we want to keep those moving through the air good. We don't want to disrupt the airflow going over those. So we move the flaps to the middle, right next to the fuselage. They come down, and then that'll help direct more air straight down underneath the body of the wing. That's also why they don't talk about it in this chapter, but when you are landing, you'll actually get some ground effect. And so pretty much about the width of the wing of the airplane when you're that high off the ground. So let's say your wings are 30 feet wide. When you get to about 30 feet off the ground, you're actually going to start building a cushion of air underneath, and then when you put the flaps down, that downwash will interface with the ground effect. And if you're not careful, when you're a beginning pilot, usually what will happen is you'll come down, and then all of a sudden you'll get close, and you'll kind of almost bounce off that air, that cushion of air. So you have to kind of lower the nose back down to keep yourself coming down. So that's what we use flaps for, so we can control the aircraft at slower speeds. Okay. Now, the propeller. I think this is actually our last slide. So, propeller. So, a propeller, if you really look at that picture, it's actually four wings, really, right? And so, and also if you think of a propeller, where is the fastest part spinning, right? It's at the tip. So, the slowest part is at the actual center. And as you get further and further to the tip, the faster it's going to go. And so, when you look at a propeller, that's why you'll see that twist. You'll see that twist in it, just like that picture shows you, because you want to be able to grab more air when you're going slower, and you want to be able to slice through the air. You want to grab a little less air because you're going faster. So that's why the propellers. Now, if you're in a helicopter, now we don't have a lot of helicopters in CAP, so we usually talk about aircraft. But if you're in a helicopter, what's a helicopter? Helicopter's propeller, it's just sitting on top, right? So it's just sitting on top. It does the same exact thing as a propeller. It is a propeller. And so what happens with a helicopter is it can control the pitch of all those blades. And that's what allows the helicopter to move in place as it's basically hanging underneath this propeller. All right. So that is the end of chapter 1. So again, now you should be able to do these 5 things. So you should be able to describe the relationship between Bernoulli's principles and Newton's laws of motions. Remember, especially that third one, and how they were used to develop a machine that could fly. Describe the coefficient of lift. So coefficient means, all the different ways. There's not just one thing that's making that airplane, that wing, lift up in the air. There's lots of them. And so, what are all those parameters involved? And then identify the parts of an airplane and the airfoil. Describe the 4 forces of flight. And finally, the 3 axes of movement that we talked about. All right. In addition to all that, you may want to pause the screen here and take a look at these words and their meanings. You really should be able to identify each of these words and what they mean. So some of the words here that you want to pay special attention to is like chord, which is a line that's drawn through an airfoil from its leading to trailing edge. Most people have a hard time understanding what chord is. Vortex is another one you're going to want to spend some time on. Most of the rest of these you should be able to understand relatively easy. We talked about downwash quite a bit. Make sure you understand downwash. And okay, that is it. So questions. So if you have questions, go ahead and put the questions down in the comments section down below. Just remember that any comments you put on there are likely to be seen by lots of CAP members, especially some younger members. So always make sure that your questions are appropriate for our younger cadets. If you wanted to say something more directed, feel free. You can send me an email myself, and that's it. So with that, I want to thank everybody for your time tonight, and we'll see you for Chapter 2 in about a week. Thanks so much. Hope everybody has a great night. Bye.